Hello, everyone. This is Muhan Shao from Johns Hopkins University. Today, my topic is dynamic palatogram generation from Cine MRI for normalized speech assessment. Tongue palate contact patterns during speech tasks have been broadly investigated in the study of speech production. These patterns can be analyzed to investigate the development of lingual kinematics during speech production. Additionally, these patterns are beneficial in diagnosis and treatment of pathological speech disorders. The contact information could also contribute to speech synthesis. Here is an example of tongue-palate contact patterns for normal English speakers. The left image shows a no-contact situation, and the right image is the contact pattern with saying t, as in top. The red region shows the contact region. Static palatography has been used to generate a graphic representation of the tongue's contact with the palate during a specific speech task. This method generally includes 3 steps. First is to apply a recording medium to the tongue. Second is to let the person say a specific word, and then takes a photo of the palate. Here is an example of the palatogram. The obtained palatograms provide spatial tongue-palate contact information. However, it doesn't assess the tongue's contact with the palate over time, for example, during a speech phrase or swallowing. Besides, the recording medium usually tastes unpleasant. Another technique to generate palatograms is electropalatography. To produce a palatogram using EPG, the speaker is fitted with his or her own artificial palate with touch-sensitive electrodes. Here is an example of the artificial palate. Then, the person is asked to say a specific word and repeat it several times. The reading EPG system is used to record the tongue-to-palate contacts and the corresponding acoustic signal during the assessment. Here is an example of the tongue-palate contact pattern observed in normal English-speaking adults. We see that EPG reveals both spatial and temporal contact patterns during speech. However, it only provides tongue-palate contact points as binary signals, but no other information about the tongue-to-palate distance. Besides, the EPG technique requires specific design of the artificial palate for each user and is quite expensive. So in this work, we want to present a method that can show the palatograms and the tongue-to-palate distances at the same time using Cine magnetic resonance imaging. Cine MRI is a fast imaging technique that provides good brightness contrast. It allows non-invasive observation of the human tongue and therefore can be used to extract and analyze tongue motion during speech. Here is a series of cine sagittal slices of the tongue during speech. We can observe that there is an air gap between the top of the tongue and the hard and soft palates, and we call this air gap as airway. When there is contact between the tongue and the palate, the vertical thickness of the airway will become 0. We can observe this contact in the last slice. The goal of this work is to generate a spatial temporal palatograms using Cine MRIs. The proposed method is composed of 2 steps. First is to segment the airway in the sagittal cine slices using a 2D U-net. The second step is to compute the vertical airway thickness in the superior-inferior direction, and then project the thickness to the axial plane. and get an MR palatogram at this time frame. By repeating these two steps in all time frames, we can generate a series of MR palatograms. The proposed method provides both tongue-palate contact points and distance over time during speech. The thickness values in the MR palatograms provide tongue-to-palate distance, and zero thickness indicates contacting point. Our datasets consist of 4 healthy subjects who are native speakers of American English. The speech tasks were the phrases "are thin," "are sook," and "are shell." These phrases were chosen because they are short enough to be captured by the Cine MRI and can provide a variety of configurations of the contact between tongue and the palate. The Cine MR images were collected in sagittal orientation over multiple repetitions of each speech task, timed to a metronome. The datasets had a duration of 1 second, and there are 26 time frames per second. The images have input resolution of 1.875 by 1.875 millimeters, and the slice thickness is 6 millimeters. The tongue data for each time frame contains a sagittal stack of 9 slices, and 5 to 6 slices per time frame contain the airway, depending on the size of the tongue. These figures are some examples of acquired 5 sagittal slices of the first time frame during a speech task. Here, I will introduce the airway segmentation network. It's a 2D UNet architecture. The input to the network is the 128 by 128 Cine sagittal slice. The UNet architecture consists of 5 resolution levels. Here shows the details of the encoder and decoder. The initial feature number of the network is 16. The feature number doubles after each resolution level. In the lowest resolution level, the size of the feature map is 8 by 8, and the feature number is 256. The output of the network is a probability map of the airway, and then it is converted to a binary airway mask. To create training data, we manually delineated the airway on the Cine slices for the phrase "are thin" from one subject and "are sook" from another subject, and used these images to train the 2D UNet to segment the airway. Here shows 2 examples of the manual masks of the airway in the Cine sagittal slices. During training, we used the data augmentation by applying random scaling, rotation, and translation to the images. The loss function was 1 minus the mean dissimilarity coefficients, and the batch size is 16. After producing the airway segmentation masks, we can compute the vertical thickness of the airway by counting the pixels in each column. For example, this figure is an airway mask, and the blue lines show the vertical height of the airway. In one sagittal slice, we project the thickness value onto an axial plane, and the mask in this sagittal slice shows a profile in the axial plane. Then, we project the thickness in all slices at 1 time frames onto the axial plane, and we get a palatogram at this time frame. In this MR palatogram figure, the orange line is the projecting profile corresponding to the airway mask in the top figure. A sequence of MR palatograms can be generated by the same steps for all the time frames. If we look at this MR palatogram, the grayscale values of the MR palatograms reveal the tongue-to-palate distances over time during the speech task, and the areas with zero thickness, which are black pixels in the MR palatograms, indicate tongue-palate contact points. Here are some visualization results of the airway segmentation. These figures show visual comparison between the automatic airway segmentation and the manual delineation from one testing subject. The left column shows the comparison at the third time frame. From top to bottom, the figures are cine sagittal slice, the 2D UNet segmentation result, and the manual delineated airway mask. And the right column shows the same comparison at the 26th time frame. We can observe that the network successfully identified the boundary of the airway. Here, this figure shows the comparison of the MR palatograms between the UNet results and manual delineation results for the phrase "athuk" from one testing subject. We only show some key time frames here, and the thickness values in the MR palatograms were normalized between 0 and 1. In each subblock, the left column shows the UNet result, and the right column shows the manual delineation result. The top figure shows the MR palatogram, and the bottom figure is the airway mask overlapped on the mid-sagittal slice at that time frame. The palatograms generated based on the UNet segmentation show similar contact patterns and tongue-to-palate distances compared to the manual delineations. We can see that at the sound, the tongue-palate contact are in the anterior portion of the palate, and the tongue-to-palate distance is large in the posterior region. At the oo sound, the contact is limited to the sides of the palate. At the k sound, there are many contact points in the center of the palate. We also want to compare the tongue-palate contact patterns between different subjects saying the same phrase. Here shows the MR palatograms for phrase "are thin" from two testing subjects at the key time frames. The airway masks were generated by the segmentation UNet. We can see that the palatograms show similar contact patterns between the two subjects. At the sound, there's a small contact region in the anterior portion of the palate. At the E sound, the contact is on the sides of the palate, and there is a large contact region in the center of the palate at the sound. And here shows the MR palatograms for phrase "a shell" from two testing subjects at some key time frames. Still, the airway masks were generated by the segmentation UNet. The palatograms also show similar contact patterns between the two subjects. The sh sound is characterized by contact in the lateral anterior portion of the palate. In the a sound, the tongue-to-palate distance is large in the center of the palate, and the L sound is characterized by contact in a small anterior portion of the palate. In this paper, we present a new method of tongue-palate contact assessment during speech using Cine MRI images. Our method first segments the airway in the sagittal cine slices using a 2D UNet. Then, the vertical airway thickness in the superior-inferior direction at each time frame is computed and projected onto the axial plane to generate a sequence of MR palatograms. The proposed method provides both tongue-palate contact points and the tongue-to-palate distance during speech, which could help better understand the speech generation. And the study of speech production is beneficial in diagnosis and treatment of pathological speech disorders. For example, the tongue-to-palate contact and distance information could improve the design and evaluation of prosthetics for speech therapy. That's all for my talk. Thank you for your listening.